Okay. Sorry, what's the CCHILI? Thank you.
Thanks everybody for coming back from the extremely slow, sequential, non-parallel coffee line. It is my great pleasure to introduce our second speaker, who's Bingbin, and it's a little funny introducing Bingbin because she's just starting a postdoc, but actually I'm expecting Bingbin to be writing letters for me very soon. She finished her PhD at CMU with Andrei Rostesky, and we're very fortunate to have her for a semester as a research fellow in both programs. She's actually contributing a lot and running a lot of things behind the scenes. She's one of our main organizers internally now. So, you know, when she's on the job market in a few years, bad news for you, she's already been hired by all the top schools, so try to hire her faster than that. And she's known for a lot of things, but she's been one of the key people working on the theory and the practice of kind of the frontiers of transformers and transformer-related questions. So I'm very happy to learn from her. So please welcome her.
Well, thank you so much for the very kind and very generous introduction. I hope I'm able to tell you something interesting in the talk. So I think we all know that transformers, they are very capable, but they also have some mistakes. So in today's talk, we're trying to see if we can take a deeper understanding about some capabilities and also limitations of these transformers in sequential reasoning tasks. And this is based on some joint work with several collaborators. Many of them are here in the audience. All right, so, oh, I'm sorry, I think I clicked the wrong button. Great, so the plan for today will be like this. So we'll first briefly define what we mean by sequential reasoning, and then the talk will consist of two parts. In the first part, we'll talk about some theoretical results about how shallow transformers can implement long sequential reasoning chains. And here we'll use some tools from Krohn-Rhodes theory and also formal languages. Then for the second part of the talk, we'll talk about some practical results where we look at OOD problem of transformers. All right, so the focus for today is sequential reasoning. What do I mean by that? One example is, say I'm trying to multiply several numbers together. Then we can do this one by one, and this is sequential. Another example would be multi-hop reasoning, where we apply a chain of deductions. Sequential reasoning also show up, say, if we're trying to track the value of a variable in a for loop. We can see that all the sequential reasoning tasks, they take a very diverse forms. So one way to formalize it is to take one aspect of it and think of it as sequential state transitions. To show you what I mean, think of the multiplication task we have here. In order to compute the product, we can instead write 1 and -1 as -1 to the power of 0 and 1, and then trace how the exponent changes. We can do this using a two-state machine, where the two states are the exponents being even or odd. If we see the input 1, then we toggle the state. Otherwise, we don't change the state. So this two-state machine is called a parity counter, and it's one of the small example of a finite-state automata. Finite-state automata in turn sits at the bottom of the hierarchy for all automata, but for today, we're only focusing on finite-state automata. Right. So formally, a finite-state automata A is defined with three components: the state space Q, the input alphabet sigma, and the transition function delta. At each time, the transition function delta will take in the previous state Qt -1 and the current input sigma t, and transition to a new state Qt. We consider finite state automata, so Q is finite. One example is the thing we just saw, that's a parity counter. Here, the state space and the sigma are both binary. In another example that we'll see later, we have a one-bit memory unit. Now we still have two states, but now we have three inputs. If we see the input club or diamond, then we set the state to be club or diamond. If we see no op, then we don't change the state. And the reason we're calling this a memory unit is that we can think of club or diamond as writing one bit information to the unit, whereas no op is the same as reading from the unit. Now, having defined automata, the task of reasoning will correspond to simulate the state transitions in these finite-state automata. By simulating, I mean that we're trying to learn a sequence-to-sequence function where the input sequence consists of the elements from the input alphabet sigma, and the output sequence consists of the state that the automata will go through upon seeing the inputs. We will consider two modeling choices. One is transformer, and the other is RNNs. Our focus will be transformers, so I'll give a quick recap. So for each transformer layer, we compute the output by taking a weighted sum of all the tokens from the previous layer. And then we'll pass the weighted sum into some fully connected part. The weights we use are called attention scores, and these are normalized to sum up to 1. I'll show two extreme cases of the attention patterns. One is the uniform attention. In this case, the current position will attend uniformly to all the previous positions. Another extreme will be sparse attention, where we put all the attention weight on one sparse location. In terms of functionality, we can think of the uniform attention as taking the sum or average, whereas the sparse attention as performing some sort of selection operator. Okay, so back to comparing these two. For RNNs, each computation unit is going to be unrolled across time sequentially. We can see that this is quite natural for modeling the transition function because each unit can be considered as corresponding to the transition function itself. On the other hand, for transformers, each computation unit is now a layer, and this layer is computed in parallel across all positions. The only sequential dependency in a transformer will be across the layers. And typically, the number of layers is much smaller than the sequence length. For example, for the biggest model these days, we have about hundreds of layers, but we have thousands or hundreds of thousands input length. Then the question is, how can a parallel model like transformer model this kind of long sequential reasoning chains? We'll show an example using parity. The point here is that in order to simulate the automata, there are usually more than one way to do this. For instance, for parity, we know at least two solutions. One is an iterative solution, where we say that Qt can be computed as the XOR of Qt minus 1 and the current input sigma t. We also have a parallel solution, where we can compute Qt as the sum of all the previous sigma t, then take the mod 2. If we try to write out the computation graph for it, then we can see that the iterative solution have this kind of form, which is quite natural for RNNs to implement. On the other hand, the parallel solution will give you this form, which is very reminiscent to a transformer layer. We can also trace the longest sequential path in these two graphs. For the RNN solution, the biggest path length is t, whereas for transformers, the path length is 1. In the following, we'll call this kind of solution with sublinear in t number of sequential steps to be a shortcut. All right, so our goal for the next few slides would be to understand what are possible shortcuts that transformer can implement. We'll look at two shortcuts. One is log t layer solution. For this one, it's already an exponential improvement over t. In the second case, we can see that we can even do better and remove the dependency on t altogether. This will be a q-square layer solution. In the following, we'll see what kind of structures are required to implement these solutions and why is transformer suitable. All right, we'll start with the log t solution. Recall that our goal is to learn the mapping from the initial state q0 to the current state qt, where this mapping is given by a composition of functions. Each element in the composition is now a partial application of the transition function on the current input sigma. So now we have a q to q function. And because q is finite, these functions correspond to matrices, and function composition corresponds to matrix multiplication. For instance, for parity that we saw earlier, if we have the input 0, then this corresponds to the identity matrix. Whereas if we have the input 1, then we get a swap matrix. Then because function composition and matrix multiplication is associative, we can compute the composition by building a binary tree, where each node in the tree will compose its two children. Importantly, the nodes in the same level of the tree are computed in parallel, and the only sequential dependency will be the tree depth. In this case, the tree depth is log t. And I want to note that here we have a depth-width trade-off in the sense that if we don't build a binary tree, but I'll say like a k-ary tree, then you will pay shorter tree depth, but your width will be higher. So the width for MLP will grow. All right, so that's the log-T-linear solution. We saw this construction in Daniel's talk, and this kind of construction is also used, for example, in speeding up the training for linear RNNs. All right, so next question is, how can we do better than log-T-layer? We actually already saw one example of this, and that is the parity case. For parity, we can compute it using one layer regardless of the length of a sequence. In general, this kind of idea would apply if the function composition is also commutative. But commutative would mean that the order of composition doesn't matter. So the only thing that does matter is to count the number of occurrences. And this counting operation can be done in O1 layer. So overall, we can do this in O1 layer. Then how about the case where the function composition is not commutative? In this case, the main idea we will use is to decompose the task into something simpler. I'll give you one example of decomposition. Say now we have some automata that is a car driving a circle. The state space consists of two parts, the direction of the car, which can be clockwise or counterclockwise, and also the position of the car, which can be one of the four values in this case. The car can either drive one step forward or make a U-turn. First, we can check that this is not commutative, because if we drive then turn, then the state is not the same as turn and drive. Our goal is to see how can we find the final state, assuming that we start with the initial state of clockwise and position 0. Now, the idea of decomposition is to break this down into two steps. In the first step, which we realize that in order to compute the direction of the car, we can do this by solving a parity task on only the turn operations. And this can be done in O1 layer. Then once we have the direction of the car at each step, computing the position is also easy, because now we can take a signed sum of all the drives and then take the mod. The sign is given by the previous step, and the sum and mod can both be done in one layer. So overall, we have two operations of O1 layer each, and that's the idea of decomposition. More generally, we need to figure out what is the object that we're trying to decompose. And the object we're decomposing is called the transformation semigroup. This T of A is defined as all the elements of the partial application of the transition function and also their composition. And just a quick reminder, a semigroup is a generalization of group, which is now only required to be associative. To show you what I mean, for the parity counter, the corresponding T of A consists of two elements, and this one will correspond to the cyclic group of order 2. However, for the other case we have, the memory unit, if we try to write out the function for, say, the clap operator, then now this function is not invertible. So that's why we need semigroup rather than just groups. Now we know that the object that we're trying to decompose is the transformation semigroup. We can apply Krohn-Rhodes theory to show that for a fairly wide subset of A, we can decompose them. We can decompose their T of A into two base vectors. These two base vectors can each be represented by one transformer layer. The first one is a mod counter, which is a generalization of the parity counter. For the parity counter, we have mod 2. And for the mod counter, we have the mod for some general prime. The other base unit is a memory unit, which generalizes over the 1-bit memory unit. For the 1-bit memory unit, we have 2 states and 3 inputs. For the general case, we have Q states and Q plus 1 inputs. The first Q value will set the state to some value, and the final input is the reading from the state. Why transformer is suitable? Because each of them correspond to one transformer layer. For example, the mod counter can be implemented by the uniform attention, where we just take the average of all the things before. The memory unit can be implemented by one layer of sparse attention, where the attention will sparsely attend to the most recent non-read operator. We can also show that the number of factors is going to be bounded by Q squared. And since each factor is implemented using O1 layer, the overall number of layers is also Q squared. I want to pause to see if there's questions.
You're saying this is for some subset of automata.
Yes. I'm sorry?
This is some interesting subset of
Oh,
automata.
yeah. Right. So the form definition will be solvable. And that means that, so for the automata, there are some, okay, so T of A can be decomposed into something simpler. It's a simpler version of semi-automata. And then associated with that semi-automata, there could be either a trivial group or some group. If the group itself is solvable, then we call it solvable. So by solvable, we mean that some decomposition has some nice property that all the decomposition factors are abelian. It's a special case, but I guess it's still fairly general subset. Yeah. Okay.
I mean, just building on that, can you give some intuition for like the marginal cases, the hard things that are solvable, or the easy things that are not solvable?
Oh, okay. Yeah. I guess to make sure I'm following questions, since you're saying like if there's any example of non-solvable ones, yes. So one thing is the symmetric group of order 5, so it's S5, and that is you're taking permutation of 5 objects, and that thing's not solvable. Okay, so if there's no more questions, that's the end of the first part. So we saw this 2 solutions. One is log T-layer solution, which used the fact that function composition is associative. For the other solution, we have Q-square layers, and this will use the structure of the transformation semigroup. And I guess kind of building onto the 2 questions that were asked earlier, one question we can ask is, can we do better than log T-layer in the general case? And the answer is likely not. And that's because constant depth transformers belong to TC0, which is some complexity class. And this has been shown by both Will's work and also some other people's work here. However, there are some automata that we know is NC1 complete, for example, S5. So this means that unless TC0 is equal to NC1, which is Krohn-Rhodes open, it's not possible in general to get a constant layer solution for all automata. I also note, I also want to note why transformer is suitable. So first reason is that it has parameter sharing. For example, compared to a circuit, transformer has weight shared across all the positions. So the size of the transformer will not grow with the sequence length. Another interesting fact is that transformer is very parallel. So this means transformer can implement some solution that is shorter than what is given by Krohn-Rhodes. One example we already saw is that for all abelian groups, transformer can implement them using O1 layers, independent of the size of the group or the sequence length. We also found in the special case of non-abelian group, we can also solve it in O1 layer. So there's some structure in the transformer that's more interesting than what Krohn-Rhodes theory can tell us. All right, so these are all representational results. We're saying that there exists some solution. Then the next step is to see, can we take these results to learn better about the practical solutions? I guess a priori it's unclear whether we can find these solutions in practice. So that's the first thing we want to check. To check this, we run experiment over various automata and also transformer depth. Now in the table, each row corresponds to one automata and each column corresponds to one transformer depth. Here, lighter color means better performance. We can see that for all automata, there is some transformer that can solve it perfectly for indistribution. Moreover, the rows of the table are roughly ordered by the difficulty of the decomposition. And we can see that roughly the number of layers required in practice follow the trend of the decomposition depth. In particular, at the bottom, we have 2 non-solvable automata for which the Q-square layer solution doesn't apply. And we can see that for these 2, we indeed require more layers to learn in practice. However, this is not to say that the solution in practice are the same as the constructions. For instance, one reason is simply that we have more than one construction. In fact, in many cases, we can have infinitely many solutions. And I'll show one example with the automata at the top. So I think there's a question, or yes, please.
What width are you using for these transformers, and how did you choose it?
Oh yeah, I think the width we're not changing. It's probably 256 or something.
The plot look the same as you vary the width?
For this one, I'm not sure we varied the width a lot. I'm guessing that, so there will be some trade-off in the sense that if you, okay, I think width might not affect the representational power, but it does require training. So I guess like for bigger width, the training will be better. For example, here you can see that for C2 or C3, these are technically solvable in one layer, but the performance here is pretty low, and it's probably because training is hard.
So you're talking about automata, these labels all correspond to small finite groups. Are these automata that specifically compute the group operation there, or this computational instance?
Oh, yeah. So here we are giving the input as elements from the group, and then the labels are also the corresponding composition of the group elements. So these are precisely following the input at the alphabet and output at the states. Is there any question?
Yeah.
Okay, yeah, thanks. Any other questions? Okay, so if not, I'll tell you about the infinitely many solutions for Dyke. So Dyke language consists of sequences of balanced parentheses. For example, this is a valid Dyke sequence, but this one is not, because the two closing brackets are swapped. We care about Dyke because they represent the hierarchical structure that naturally occur in both programming and natural languages. We know that Dyke can be processed by a stack, where we can push to the stack all the open brackets and pop them out when we see a corresponding closing one. Prior work has also shown that Dyke can be implemented by a two-layer transformer. If we visualize the attention pattern of the second layer, then it seems that we can extract the stack algorithm. So here is the attention map, and the way to read this is that each row corresponds to the attention pattern for one position. For instance, this is the attention pattern used to predict the closing square bracket. And we can see that for this one, the attention pattern is correctly identifying the correct open bracket. However, in general, more often than not, we don't see this kind of stack-like patterns. And there's probably a reason for it, and that is there exist an infinitely many solutions that can solve Dyke. And this is true even when we're using a two-layer transformer and we're constraining the output of a first-layer transformer. In our paper, we characterize some condition which we call a balance condition that is both sufficient and also necessary for this kind of two-layer transformer to solve Dyke. I'm not going to formally define this, but we can think of this as a transformer's implementation of the pumping lemma for regular languages. So the idea is that you can always repeat some part in the sequence, and then the repeated sequence is still in the language. One implication of this is that now the attention pattern can be misleading. There are many attention patterns that can satisfy the balance condition, but they are not informative of the structure of the task. In particular, the uniform attention can also be used to solve the task, but this is not reflecting the hierarchical structure. Then we can also use this balance condition as a regularizer in practice. So say now we are trying to see how the transformer perform OOD. These are the trained transformers. They perform a 100% in distribution. And now we're trying to check their length generalization performance. The x-axis corresponds to the OOD accuracy, where further to the right is better. The y-axis corresponds to the amount of violation to the balance condition, where lower is less violation. If we train in the default training, then we see that transformers violate the balance condition, and also they achieve poor OOD accuracy. When we add a regularizer to it, then we can simultaneously enforce the balance condition and also improve the OOD accuracy. So this is, to wrap up this part, we're saying that the construction we saw earlier may not reflect practice, because in practice, there are infinitely many solutions. But the understanding we have from the properties of these solutions can still help us with practice, for example, by improving OOD. Yes, please.
Here, infinite solutions, you mean for Dyke up to a constant length?
Yes, so we're currently considering bounded Dyke. Yeah, so bounded Dyke will be regular languages.
And the balance condition is if and only?
The condition is actually slightly different for both directions, but yeah, like For some condition, it's going to be sufficient. For some slightly changed condition, it's going to be necessary. Any other questions?
When you enforce balance, do you get the attention patterns to look different, or it's still go back to those parts of the attention pattern, or does it not?
Okay, yes, great clarification. So I guess like here, attention pattern has nothing to do with being balanced or not. For example, uniform attention is perfectly balanced.
Yeah, so in practice, what happens generally when you actually add this regularizer?
Yeah, it's very hard to find the stack pattern. Yeah. So even if we try to enforce, we don't see the stack pattern pop up. Yeah.
You mentioned the stack pattern specifically works because this is a regular version of Dyke, right?
Oh, I think the stack pattern would work because we can think of stack as the solution to this problem. So I think the deepest depth for Dyke in this case will be if you have sequence length to be n, then you have n depth. And I guess like prior work they show that you can have n, but I think in that case your precision needs to be unbounded. Yeah. But to clarify, for our setting, we only consider bounded Dyke. Yeah. Okay, if there's no more questions, then we'll go to the empirical part, which would be to have a better understanding about why transformers struggle with OOD. For this case, we'll consider a very simple setup, which is a variant of the one-bit memory unit. Recall from the previous part of the talk that the memory unit is one of the two base vectors that we can get from Krohn-Rhodes decomposition. Then for the particular one-bit memory unit, it also has a name called flip-flop. So we'll use this name in the following. We define flip-flop language as the language consisting of sequences of instruction value pairs. There are 3 instructions: read, write, or ignore. Each instruction is followed by a binary value. There's no constraint to the value except that the value following the most recent, the value following each read will be the same as the value following each the most recent write. And the reason is that we're thinking of this as writing to the memory, and then we're reading from the memory, so the value should be consistent from the last write. One example is this. So here, the first read should be following the most recent write, and the value is 1, and that's correct. In the second case, the read value conflict with the write value, so this is not a correct prediction. On flip-flop language, we can define a task where we train and test on predicting the value following the read. That is, we're providing supervision only on these 2 positions. We can define a different task where we just simply do next word prediction. But I think this definition will be a simpler and easier task because the task is now deterministic, and also we don't need to worry about the supervision signal getting overwhelmed by those irrelevant tokens. And I said that we're checking OOD performance, so I need to define what is the data distribution. The data distribution is parameterized by the probability of seeing ignore, and that's P of I. We will vary P of I during train and test time. The other 2 instructions will split the remaining probability mass. And we also set equal probability for 0 and 1 value. In the experiments, we always fix the sequence length to be 512, so there's no length generalization. Okay, before I show you the results, I want to try to say a bit more about why flip-flop. So we know that flip-flop is a variant of the one-bit memory unit, which is a simple atomic unit that underlies many reasoning tasks. One example is that flip-flop can be considered as a simpler version of the induction head. For induction head, we want to find the most recent occurrence of the current token. For flip-flop, it's simpler because we're always looking for the same previous token, and that is the write. For example, in this case, we're finding the most recent write than the previous one. We can also think of the flip-flop as modeling the long-range dependency. For instance, if we put the sequence to be extremely sparse in writes, then the model will be required to look far back in the history. Flip-flop is also a toy model for closed domain hallucination. By closed domain, I mean that now the prediction will directly contradict the context. For instance, here, the only error mode for flip-flop is when these conflicts happen. The error in flip-flops in general will imply errors in some other more complicated cases. For instance, prior work has shown that transformers' performance will struggle when we have irrelevant context or when we change the semantics of some token. For irrelevant context, we can think of this as adding more ignores. And for changing the semantics, we can think of this as writing to the state, so that we're changing the value of the state. Okay. I hope I've convinced you that being such a simple task, the errors in flip-flop would also imply the error in more complicated tasks. So even though this task is very trivial, we still have reason to care about it. Okay, so now these are the results. We're going to train flip-flop by setting P of I to be 0.8. Then for test time, we're going to increase the P of I to 0.98. And that is, we're trying to test on sparser sequences with fewer lengths. And remember that we're always fixing the sequence length to be 512, so there's no length generalization. To convince you that the task is actually very easy, note that we can drive both the in-distribution and out-of-distribution error to be 0 within 200 steps of training an one-layer LSTM. In comparison, transformer will require much more steps to train. Here, each panel corresponds to one configuration of the transformer. The default configuration will be this one, where we have 6 layers, 512 dimension, and 8 heads. But we vary all 3 dimensions in the experiments. You can see that for all transformers, they can do pretty well in distribution, and these are the gray lines. However, their OOD error is much higher, and these are marked by the red lines. This is especially bad when we compare to the LSTM, which can reduce error very, very quickly. I also want to note that the in-distribution error is, the OD error is actually not very bad. So the y-axis is log scale. For most of the models, we can, the model can achieve about 99% accuracy or above in most of cases, but it still have occasional errors. We will call these occasional errors as attention glitches. In other words, these attention glitches correspond to imperfect hard retrieval. The previous slide tells us that whereas the LSTM can solve the task perfectly, transformers have a long tail of errors. And these errors don't easily go away if we scale up the model. For instance, we can play the same game with ChatGPT. We can explain the game to it, provide one example, and then ask the model to complete the new sequence. And then we're still using the sequence of 12, so it's the same as the one that we did in the experiments. For GPT-4o that I tried this weekend, 10 tries on the same sequence, the prediction is exactly random guess. So we have 50% accuracy. So I think this tells us that the current model is not very robust at this kind of task. I also want to note that GPT-01 mini got 100% accuracy. So it's very probably just one more piece of evidence that they're probably doing something interesting there, likely more than just transformers. All right, so now we know that these attention glitches exist and persist across scales. Can we understand the cause of it? First, note that the cause is not representational power, because we know that attention glitches, flip-flop can be solved by 2-layer transformer with 1 head. We already saw this in Daniel's talk and also in Alberto's paper as well. Now, what is the cause? We identified 2 potential causes. Each will be related to one type of OOD error. The first of error can happen when we go to denser sequences. That is, when we're trying to put more things in the denominator of the softmax. We call this failure mode the diluted soft-attention. The diluted soft-attention, because now the max value of the softmax will be pushed further away from 1 when we add more items to the bottom. This failure mode has been identified in prior work, and one potential fix to this is to switch to a hard attention. But note that even though hard attention can solve this particular failure mode, it cannot solve the other failure mode, which is when the argmax itself can be wrong. And this could happen when the position information dominates the prediction more than the token itself. To show you that this happens, one example is that if we train on a very simple memory unit, then here's the attention map for it. This is a very sparse sequence where the error only happened at the where the write only happened at the very beginning of the sequence. We can see that the model will correctly attend to the beginning of the sequence for a very long time until the very end, where the position starts to dominate. Okay, so these are 2 errors. What are the mitigations? We tried two main types of mitigations. The first one is about scaling the data or scale, and the other is some more indirect controls for the algorithm. For the data part, one thing is to use OOD data directly during training. And this should serve as the performance ceiling. And indeed, this works. And it can work pretty well, even if we only have a few samples. We could also try straightforward scaling of the resources. For this case, we can try to increase the model size, the sample size, and also training steps. For the indirect control, we have regularization, which includes both the standard ones as weight decay or dropout, and also trying to specify the attention, which is specific to the task we're solving. We could also try to tweak the architecture, for example, by changing the position encoding or changing the activation function. So we tried a bunch of things and their compositions. And the summary is that along the two OOD errors, we're not improving by much. Now, in this plot, the x-axis correspond to the OOD error on denser sequences, and the y-axis correspond to the OOD error on sparser sequences. The error is smaller if we go left or go down. Now, each point is one train transformer. And we can see that all of them are pretty far from the origin, which is the zero error corner. In contrast, a small one-layer LSTM can solve the task perfectly. Okay. I'm trying to dive deep into the other mitigation, but for the interest of time, probably will skip a little bit. So basically, the main takeaway is that this tiny task is surprisingly hard to do perfectly. We tried a bunch of things, and some mitigation can help with one type of error mode, but not both. So in the two panels here, the top panel corresponds to the error on the sparser sequences, and the bottom panel corresponds to the error for the denser sequences. We see that the gray violin correspond to the baseline model, and the two green ones are the errors from LSTM or OOD training. So these are the performance ceilings. Scaling doesn't help much. It can help a bit with sparser sequences, but not denser ones. Similarly, for various regularization we tried. One thing particularly I want to highlight is that embedding dropouts seem to work particularly well on sparser sequences. And we hypothesize that it's likely because now we're breaking the correlation between position and the prediction. Training positional encoding can help on denser sequences, but not sparser. And similarly for this, combining various things that either work for sparse or dense still don't fix both. So the takeaway is that it's a very simple task. We tried a bunch of things, but we couldn't fix it. And what's the takeaway? So the takeaway is that for this OOD error, one simplest test that we can use is this flip-flop. And then for this very simple task, we identify something called attention glitches. For attention glitches, we saw that transformers have a long tail of errors, which are not present in small RNNs. So making transformer as efficient in learning for RNNs would be one realistic goal for the future. And also, the error seems to be inherently related to the limitation of transformers. We're not able to fix it, but maybe using data is helpful. And this data aspect seems to be the current theme in the program. Okay, so that's going to be the end of the talk. So we saw two parts. The first part, we saw how transformer as parallel model can solve sequential reasoning tasks. And in the second part, we saw some limitation of transformer exposed by these attention glitches. I also want to make one last semi-meta point that I think the point of the workshop is to bridge together theory and practice. And I think one way we can do this is by studying this kind of proper abstraction or simplification of the problem. We can see that these problems are good for theory because they are simpler to be analyzed. In this work, we mentioned some results from the automata theory, and we will see multiple talks from the workshop also using multiple other tools. On the empirical side, these very simple setups are easy to run experiments on, and these are very cheap experiments. We can test them thoroughly. We saw some example where we use some theory-inspired setup, such as the flip-flop language, but there could be more things we can do. And empirical results can also guide theory. For example, the O1 layer construction for the non-abelian group that we mentioned earlier is actually inspired by peeking into a train transformer. So I think this will be a good place where we can take benefits from both communities. Yeah. With that, I'll end my talk, and thank you for your attention, and thanks for my collaborators again.
We have a couple of minutes for questions. Yes, please.
So a two-layer MLP can compute the operation on SI at a distribution perfectly. So,
Sorry, what do you mean? Two-layer
so
MLP?
when you're showing the automata, like early on in the talk,
Yeah.
and like very deep transformers or reasonably deep transformers were not able to do the group operation.
Yeah.
So like a two-layer MLP can learn that group operation perfectly. So
As in, for what width?
for S5.
Oh, sorry, for the width MLP? Sorry, are you saying some other results or the results I showed earlier?
So you were talking about automata being learnable by transformers or not being learnable by transformers and how the performance improves as the depth increases.
Yes. Yeah.
And so a two-layer MLP can learn S5 perfectly, even though the transformer models were failing to do so.
Oh yeah, the problem with that is that you need to grow the width of the model for the MLP.
What's the sequence thing?
Yeah, for example, like if you have sequence of t, then MLP needs to, the input width needs to at least grow with t. So that's kind of similar to saying the circuit part. You can solve it using a circuit, say like NC1 circuit. But the problem with the NC1 circuit is that when you add more things in your sequence, your circuit size has to grow. But the transformer is which was.
One transformer for all sequence lengths. It's one MLP for each sequence length.
How doesn't every group operation and a specific group have the same sequence length?
Oh, no. So you can put, so say, okay, in this case, I guess we can think of each element in the group as one matrix, for example.
Okay.
And then you can keep multiplying the matrices.
Sorry?
You can keep multiplying the matrices so that you can end into different elements in the group.
Oh, so you're doing many consecutive operations. You're not
Yes.
doing two operations.
Yes.
Okay.
Yes, yeah. And then the many consecutive operations is the sequence length t. So if we're doing t steps, then we have t inputs. Then for the case you're describing, a circuit or an MLP will require the size to grow with t. But transformer
Yeah. Okay. I didn't realize that you had many operations. So.
Okay. Yeah. Okay, please.
Do you have any thoughts about autoregressive generation with semi-automata? These are all just next to a prediction. What happens?
Oh, I think we didn't precisely try generation, but we did try scratchpad or like chain of thought for this kind of task. And we see that, for example, over here, transformers are not perfect, especially for OOD. But if you add chain of thought, at least we can make the things that we tested on to be 100% accuracy. So in this particular task, I think the recurrence inductive bias is very beneficial.
Thanks for the talk. I'm wondering about the connection between this like attention dilution and failure of hard retrievals and then practical length generalization issues in transformers. So do you think that like you could solve this problem by changing the architecture, let's say, that length generalization in practice would get better, or do you think there are other factors that
I would say, okay, I think there should be other factors as well. But even for the two failure modes that we identified, we're not able to solve both of them simultaneously.
Sure.
That seems problematic because like for all the mitigation we tried in the end, you see that some of them can improve on the sparser sequences, but not denser ones. Some are the other way around. We weren't able to find anything that's solving both. So I'm wondering like if in practice there are very likely more complicated failure modes for more complex tasks. If we can't even solve this, I'm not confident that we can solve 100% of those cases as well. Yeah. But that's probably saying that we need to do something with either a data or some other.
Yeah. The last like violin thought thing that you showed, where is the variance coming from?
Oh, the variance comes from the fact that for each setup we did, we tried 25 different seats.
Okay.
So that we're getting some. Right. So we're plotting, say, like the mean and the what's that called? Context. Yeah, context. Yeah. Yes, please. Thank you.
I had a question about this failure mode that you identified as simple failure mode. Is that, how common is that to identify these failure modes? Is this one of many examples, or is this, doing towards figuring out these simple failure modes after
I see. So to make sure I'm following the question, so you're saying like, is this the only task where we can expose the failure modes?
Yeah, have people been studying this? Is this endeavor, or is this really beginning?
I see. I think similar. Okay, I guess if we take the higher level takeaway of this, the one thing is the so for self-attention, I think so. For example, David's paper, he already mentioned this as one of failure mode. So that's this. So that's paper here. So there, the idea is that they have an even simpler task where we are only trying to output the first element in the sequence. And over there, you already have a problem if your attention starts to be diluted. So I think this failure mode would show up more generally, and we're not the first one to find this. And then for positional encoding as well, I think the meta point here is that the position encoding can be problematic if you go to some combination of position that's not seen during training. So know that here we're seeing this failure mode even though we're not changing the sequence length. So even for same length generalization, there are still some phenomena that's related to the positional encoding not being properly used that can cause problems. I think people realize that positional encoding is a really complicated thing, so there has been a ton of paper on that as well. So yeah, I think these are, so we are trying to show that these two problems are parts of the cause for this particular simple task, but they also show up more generally in practice.
And so it would be probably close to a classification of simple failure modes that might give us insights into what's.
I see. That's a good question. I'm not entirely sure. Okay, so another thing to note is that here we're only talking about two failure modes of attention itself. There are also failure modes for the MLP part. For example, we know that MLP cannot generalize non-linearly across the training domain, and that's because we're using Mellon. So that's actually the failure mode, for example, for learning parity. For OOD test for parity, we have that problem because of the MLP. And this task is showing the error of the attention, not the MLP. But each part of the transformer can have some different failure modes. Yeah.
In the interest of time, we can take the questions offline. And thank Bingbin again.
Thank you.